I'm going to redraw the resultant vector here. I'm going to redraw the resultant vector here because this diagram is starting to get kind of clogged and congested. But this is just the same vector as this resultant vector over here. But now we figured out that its overall eastward component is 3.9 meters east, and its overall northward component is 5.7 meters north. So the overall resultant is 3.9 meters east of the initial point and 5.7 meters north. Now, what if what we mainly care about is the length of this overall displacement? Well, it's not too hard to use the Pythagorean theorem to figure out how long that is. 6.9 meters. Overall, we are 6.9 meters from where we started. We could say that we're 3.9 meters east and 5.7 meters north of where we started, or we could just say that overall we're 6.9 meters from where we started. Again, that comes from the Pythagorean theorem, but don't worry if you don't know the Pythagorean theorem, we'll learn about that later. And finally, it might be nice if we could figure out what this angle is. Well, it turns out that you can use trigonometry to figure out that angle as well, as we'll learn later. That angle turns out to be 56 degrees. Don't worry if you don't know how to figure that out yet, we'll learn about that later. But it turns out that if you know the horizontal and vertical components, you can use trigonometry to figure out the angle and the overall hypotenuse resultant vector. So we know that overall, when the person walks 6 meters in a direction 20 degrees above the horizontal, and then 4 meters in a direction 25 degrees to the left of the vertical, overall they end up 6.9 meters from where they started at an angle of 56 degrees above the horizontal. Notice there's no way you could have gotten this 6.9 just by adding or subtracting the 6 and the 4 directly. You can't just add 6 plus 4 to get 10, or 6 minus 4 to get 2. There's no simple direct way to combine these two overall numbers. It's only when we broke things into components that there was a very simple and direct way to combine the components. So again, hopefully now we're starting to appreciate what a clever trick it is that the physicists have come up with here. There's no simple way to combine two vectors that are not parallel or anti-parallel with each other. But we can always break any vector into components, maybe horizontal and vertical components. Well, then the horizontal components will all be parallel or anti-parallel, and the vertical components as well. So those are easy enough to combine. And once we know the overall horizontal and vertical components, we can use a little trigonometry to go back to the overall vectors. In this case, we did a slightly more complicated example than before because the horizontal or east-west components were anti-parallel. But we saw that there's no big problem when two things are anti-parallel. It just means you have to subtract their magnitudes instead of adding them. All right, so I'll remind you one more time that you shouldn't worry if you didn't follow every single detail of what I just went through, and you shouldn't worry if you didn't understand how I figured out some of the numbers. I didn't expect you to understand how we got all the numbers yet. All I was trying to do here is show why components are useful and why they're such a clever trick for physicists. And again, the reason is that there's no simple way to combine two vectors that are not parallel with each other. However, if you break a vector into components, well, the components are always going to be parallel to each other. And then it's going to be very easy to combine those components. Okay, so now that hopefully we have some appreciation for why this is a useful trick, what we're going to proceed to do now is learn how we can carry out this trick on our own. How can we break vectors into components? And then once we have the components, how can we combine those to get the overall vector?